Your phone just found the fastest route across a whole city in a split second. Not the fewest roads, the cheapest by total travel time. Here is a map. Cities, and roads between them, each road with a cost. We want the cheapest route from one city to every other one. Watch it spread outward, road by road, locking in the true shortest distance to each city as it goes. This is Dijkstra's algorithm, the search behind GPS routing and network packets. Let me show you exactly how it thinks. One quick, honest note before we dig in. Everything here is free, no wall, no catch. This exact visual style is the whole idea behind my book. Algorithms and data structures, visually explained. 23 of them, each a clean diagram and runnable Python. $24, link below. Totally optional. The full explainer is right here. Now, let us go find some shortest paths. Here is the problem, precisely. We have a weighted graph. The circles are nodes, think cities. The lines are edges, roads, and each edge carries a positive cost. Pick one node as the start. We want the shortest total cost from the start to every other node. Not the fewest edges, the smallest total weight. The lazy answer is to try every possible route and keep the best. On a real map that is astronomically many paths. Far too slow. Dijkstra finds all of them at once, efficiently, with one simple idea. Always expand the closest unfinished node first. Dijkstra needs just 2 things per node, and one rule. First, a tentative distance, our best known cost to reach that node so far. The start gets 0. Every other node starts at infinity, because we have not found any route to it yet. Second, a predecessor, which node we came from on that best route. That is how we rebuild the path later. We keep the unfinished nodes in a priority queue, ordered by tentative distance. The rule is simple. Always pull out the node with the smallest tentative distance. Here is the key promise. The moment we pull a node from that queue, its distance is final, the true shortest distance, locked in for good. We will see exactly why that holds. Let us run it live. Start node A gets distance 0. Everyone else is infinity. We pull the smallest, that is A, at 0. We finalize it. Now we relax its neighbors. Relaxing asks one question. Could we reach a neighbor more cheaply through A? From A, the edge to C costs 2, so C becomes 2. The edge to B costs 4, so B becomes 4. Both were infinity, so both improve. Pull the smallest unfinished node next. That is C, at 2. Finalize it. Now relax C's neighbors. Through C, B costs 2 plus 1, which is 3, cheaper than 4. So B drops to 3, and its predecessor becomes C. C also reaches D at 2 plus 8, which is 10, and E at 2 plus 10, which is 12. Both improve from infinity. The next smallest is B, at 3. Finalize it. Through B, D costs 3 plus 5, which is 8, cheaper than 10. So D drops to 8. Next is D, at 8. Finalize it. Through D, E costs 8 plus 2, which is 10, beating 12. And F becomes 8 plus 6, which is 14. Next is E, at 10. Finalize it. Through E, F costs 10 plus 3, which is 13, cheaper than 14. So F drops to 13. Last, we pull F at 13 and finalize it. Every node is done. Notice how the frontier grew outward in every direction, always finalizing the nearest node next. No node ever needed a second look. We have the shortest distances. Now the actual route. Say we want the path from A to F. We never stored full routes, only a predecessor on each node. So we walk them backward. F's predecessor is E, E's is D, D's is B, B's is C. and C's is A. We have reached the start. Reverse that chain, and the shortest path is A, C, B, D, E, F. Add the edges, 2, 1, 5, 2, 3, and the total is 13. Exactly the distance we locked in for F. That is the whole payoff. One run from a single source gives you the shortest path to everywhere, plus the breadcrumbs to rebuild each route. Now, one hard limit. Dijkstra needs every edge weight to be 0 or positive. Here is why. Remember the promise, once we pop a node, its distance is final. That only holds if reaching it another way can never be cheaper. But a negative edge can make a later detour cheaper. Watch. A to B costs 2. A to C costs 5. And C to B costs -4. Dijkstra pops B at 2 and locks it in. But the real shortest path is A to C to B, 5 minus 4, which is 1. That is cheaper than 2. The promise just broke. So negative edges are off limits for Dijkstra. When a graph has them, you reach for a different algorithm, Bellman-Ford, which is built to handle negatives. We will not implement it today. If you have seen my A star video, this will click. Dijkstra is a star with the heuristic switched off. A star scores each node with f equals g plus h, g is the cost from the start. H is a guess of the distance still left to one goal. Set h to 0, and f is just g, the cost so far. That is exactly Dijkstra. No guess, and no goal to aim at. So Dijkstra explores uniformly, in every direction, like ripples in a pond. A star leans toward a single goal and explores far less. The trade is honest. A star is faster to one target. Dijkstra has no target, it finds the shortest path to everything from the source, all in one run. And that is why it is everywhere. GPS and map routing. Network packet routing, link state protocols like OSPF run Dijkstra to build their routing tables. Anywhere you need least cost paths. Here it is in real Python, using a heap as the priority queue. Dist maps each node to its best known distance. Previous holds predecessors. The heap holds pairs of distance and node, so popping always returns the smallest. Each round, pop the closest node. If that distance is stale, bigger than the best we already recorded, we skip it. That lazy deletion trick keeps the heap simple. Otherwise, relax every neighbor. If going through the current node is shorter, we update the neighbor's distance, set its predecessor, and push it back on the heap. When the heap empties, dist holds the shortest distance to every node, and previous lets us rebuild each path. That is Dijkstra, end to end. Let us lock it in. Dijkstra finds the shortest path from one source to every node in a weighted graph. Give the start distance 0, and everyone else infinity. Keep a priority queue ordered by distance. Repeatedly pop the nearest unfinished node. Its distance is now final. Then relax its neighbors, update any you can now reach more cheaply, and record a predecessor. When the queue is empty, you have the shortest distance to every node, and the predecessors rebuild each path. It needs non-negative weights, because that final on-pop promise depends on them. And it is simply a star with the heuristic switched off. That is the whole idea. So that is Dijkstra's algorithm. Distances start at infinity, the nearest node is always finalized next, and predecessors rebuild the route. The search living inside your GPS. We have built a real toolbox now. Big O, sorting, hash tables, trees, a star, and now shortest paths. Next, we climb one level up. Your game AI can now find a path, but how does it decide what to do? Patrol, chase, attack. That decision-making brain is a behavior tree, and it is the next video. If you want the whole picture, 23 algorithms, each a diagram and clean Python, my book is linked below. $24, totally optional. Subscribe, and I will see you in the next one.